Hello everyone, I'm Stephan van Schaik and I work on this paper together with Cristiano, Herbert and Kave. And the title of the paper is Malicious Management Unit and Why Stopping Cache Attacks in Software is Harder Than You Think. So why should you care about cache attacks in the first place? Well, I'm going to start with a very famous pyramid that's currently missing a part. And the reason why is that CPUs and memory advance every year, but CPUs advance at a very fast pace, faster than memory. And to mitigate, to solve this gap, this increasing performance gap where memory is moving farther away from CPU, there are caches nowadays. And this is kind of problematic because CPU registers at the top are very small pieces of memory, but they're really fast. And the further you go down, the slower they are and the larger it becomes. And this is a trade-off, of course. And what it means is that if you have memory that's cached, then you will have a cache hit that's very fast. But at the same time, if you have memory that's not cached, then you will see a cache miss, and that will be slower, which means that memory accesses are not performed in constant time. So what's the motivation of this paper? Well, caches are shared resources. They're shared between multiple programs running on the same CPU. They can be manipulated, not directly, but if a program loads something into the cache, it might evict something that's used by another program. This allows you to spy on other processes, and you can leak stuff like input events, but also sensitive data. Okay, so back to the pyramid. To solve these cache attacks, there are various defenses, both in hardware and software, that defend against the CPU, but they do not defend against the MMU. So to give an example, we will be talking a bit about AES today. AES is the Advanced Encryption Standard, and software implementations used to use T-tables for this, which are basically lookup tables that use the plain text combined with the key for the encryption. And the problem is with this is that the indices of these tables are key dependent. So these elements in the table may be either in the main memory or the cache, which is problematic because if we can figure out where in the cache this entry is, we'll be able to infer data of the key. So I'll give you a more concrete and practical example of this. And we'll look into prime and probe, which is one of the cache attacks. If you're interested in any of the other cache attacks, flush reload, flush and flush, or prime and abort, please read the paper. So I'll show you an example of prime and probe against AES encryption first. So this is our cache. And the cache is basically divided into different cache sets, and each cache set has multiple entries. In this case, each set has 8 entries. So we have our AST table, and every green box basically represents an entry in the T table. And we have our attacker. And in this case, the attacker is going to focus on the highlighted cache set for this situation. And the attacker has its own eviction set of physical pages. So what the attacker is going to do in a prime and probe cache attack is he's going to touch every page to fill up the cache set that he is interested in. And this phase of the cache attack is called the prime step. So now that the cache is filled with pages from the attacker simply waits until the AES encryption kicks in or something else happens on the CPU. And if you encrypt something, it will use some random entry in the T table, and that will be loaded into the cache as well. In this case, in a different cache set. So the attacker waits and then starts probing. And probing is basically the same thing as prime, except now we're going to measure each cache entry to see, or each page to see if it's in the cache or not. So this page is in the cache, this is in the cache, this is still in the cache. All of these pages are still in the cache. What does the attacker know now? The attacker knows that the AES encrypt did not use this cache set. In another case, let's say the attacker is going to use this cache set. It's going to do exactly the same thing. It's going to prime, it loads entries into the cache set, it waits, and then the AES encrypt kicks in and loads its entry into the same cache set. So what the attacker will do now is he will probe again. He will measure every page and sees the first page is in the cache, second page is cache, but the third page is not. It had to be loaded from memory, which will result in a slowdown. So what does the attacker know in this case? The attacker knows that this cache set was used. And from this information, an attacker can leak information about the key that's used for the encryption. So the question is, can we defend against these cache attacks? And the answer is yes. There are two ways or strategies to do this. One is to basically divide every cache set into a limited amount of entries that an attacker or victim or any program can use in the system. This is called way partitioning because this cache has 8 entries. It's an 8-way set associative cache. And in this case, the cache is divided into an attacker that can use 4 of the entries and the victim that can use the other 4 of the entries in each cache set. Then we have set partitioning. In set partitioning, the cache is divided based on the cache set. So you have different physical pages, and the part of the physical page will tell, of the address will tell which cache set is being used. And by handing out specific pages, you can actually divide the cache into by sets. So you basically give the upper half to the attacker and the lower half to the victim. So the question is, how does page calling work? And page calling is basically set partitioning. So we have this cache GAN, and we have physical pages. And like I said before, each page has a physical address with bits that indicate where the page is going to be in the cache set. So let's say this is a red page, and it will always be in the red cache sets. Then we have a green one that will always be in these green cache sets. And then we have a blue one that will always be in the blue cache sets. Now, if we give, for instance, as an operating system, the attacker always red pages, and the victim the blue or green pages, then these are fully isolated, shown below, shown here in the slide. So these are nicely isolated, so everything is fixed, right? Well, if we look further into page coloring, we can see that if the attacker allocates some pages, he will only allocate red pages. But if we look at the page tables, these are not typically colored by this defense. So what happens is that if you look at the page tables, is that they can have any of the colors available in the system, red, blue, and green. The question for us is, can we actually control the page tables to mount a cache attack? Well, let's meet the memory management unit. So what's the memory management unit? We haven't heard a lot about that except for operating systems, right? Well, the memory management unit translates virtual addresses into their physical counterparts, hence translate or translate attacks. And translate and probe is a variant of prime and probe that uses the page tables instead of the pages to execute this attack. So the question here is, how does the MMU actually perform page table locks? So a quick recap for if you are not familiar with how this works in operating systems and how the MMU does this. So here's a virtual address, and we have a cache again. And the virtual address consists of a page offset, which is not relevant for it, but it also contains the page table indices. So if we look at some example, these could be 4 different indices that's stored in that part of the virtual address, of this particular virtual address. The MMU itself has a register called CO3 on x86, and this points to the very first page table. And then the first index is used by the MMU, and the MMU will pick that entry from that table. And that entry will point to the next page table. And then the MMU will proceed with the next index. It will find another entry that will point to another page table. And finally, it will pick another index. It will find another entry that points to the final page table. Now, there's one index left. So the MMU is going to use that to find an entry. And this entry either tells, like, this page is present or not. And if it is present, it gives you the physical address that belongs to this virtual address. And at the same time, if you look closely at the cache, what happens is that all of these entries will also be fetched into the cache. So the question is, what do we actually need to perform a translate and probe attack? Well, first, we actually want to avoid the noise from the high-level page tables. So we have 4 different page tables that are being accessed every time. And we want to make sure that only one page table is accessed. That's our preference, basically. We also want to avoid noise from physical pages. So we have also our physical pages themselves that use our cache. And we want to figure out how to actually build these eviction sets. So let's try to tackle the first problem. The answer to the first problem are translation caches. another mythical component in CPUs that we don't hear a lot about. And what translation caches do is they store virtual addresses and the physical address of the page table they point to. So to give an example, we go back to our page table walk. So these are like the indices. We use the CR3 and we perform a page table walk. And at this point, something interesting will happen, because what translation caches will do is they will store part of the, like in this case, 3 of the indices and the intermediate page table it points to. So now this is stored, and what will happen is, okay, we have the physical address. So now if we try to look up the virtual address again with this entry being stored in the translation cache, what will happen is we'll look at the indices and take the first 3 and match it with the entries in our cache. Now that entry matches exactly with the indices we are looking for. So now we can just simply jump to the last page table. And then we can just use the last index, find the entry, and get the physical address. So we just skipped 3 of the page tables. Unfortunately, some of the properties of translation caches are undocumented. Like I said, they're quite a mythical component, and they're not really documented well. So the question we have is, how do we actually figure out the properties? How do we reverse engineer these translation caches? So back to the translation caches. So we have the indices, and what we do is basically we fix a target, any virtual address, and we basically load it through a normal page table walk and get the physical address. And what happens is our target will be in the translation cache. And to figure out the size of a translation cache, our quest is basically to access a number of other virtual addresses that will basically add entries into the translation cache. So for instance, if we try to do this for 2 other virtual addresses, then they will they will add 2 entries to the translation cache, but they will not kick out our entry. So when we load the target again, we will see that the MMU will just skip right ahead to the right page table and get the physical address. So this is very fast. So we know, okay, 2 entries is not sufficient. So let's try this with 4 entries. So we have 4 virtual addresses that we're trying to access now. And the last one will actually kick out our own entry. So when we try to reload the target, it has to do a full page table walk, which is a lot slower. So this is how we figured out the sizes of all the translation caches on 26 different microarchitectures. And the interesting part is the highlighted part of the table, which are the translation caches. The conclusion is translation caches are widely available on Intel, AMD, and ARM. So back to this picture, we have our page tables, and we are interested in the row with the hatches. We only want to control those. Well, with translation caches, we now have better control. So the first challenge is solved. So let's tackle the second one. The second one is quite simple. The solution here is we have these pages, but if we replace them by a shared page and shared memory, we only have 1 page to load, and it will only occupy 1 cache entry. That removes some of the noise as well. So the second challenge is solved. And the last challenge is to build eviction sets. So how do we do this? We drew inspiration from another paper called The Spine in the Sandbox. So if you're familiar with this or don't really remember, this is a recap. But I will explain how we build our eviction sets. And it's very similar to the description in this paper. So we have our cache. And our goal is basically we want to find an eviction set that can evict any cache set. So what we do first is we allocate a bunch of pages. Red ones, blue ones, green ones, bunch of pages. And then we draw our target. This is our target page. So what we're trying to do now is we have a red page, and we're trying to find an eviction set that can evict this red page from our cache. So every time we will load this page into the cache, and then we will try to build an eviction set. So we first draw a blue page from our set of pages, and we load it into the cache. But this does not evict our red page. So then we draw another page, and we keep trying to draw more pages until we can actually evict this target page. And then at some point, we'll end up with a set of pages that are able to evict this particular target from our cache. An annoying issue, though, is that we have found the eviction set, but we also have all these pages, these blue ones and these green ones, that are not really useful for eviction sets. So how do we filter these? The solution here is to basically remove every page. So we remove the blue one, and then we'll try to see if our eviction set is still able to evict our page. And in this case, it still is, so we can just keep the blue one out. And then we'll try the red one, and we see that, okay, this red one, our eviction set is no longer suitable as an eviction set, so we need that page. So we add it back in, and we keep doing this until all the pages are filtered. So all we're left with are the red pages that evict our target page. So now we have an optimal eviction set, and the last step we can do is basically use this eviction set to filter the remaining pages from a set of pages. So now we're just left with blue and green pages. And we can proceed doing this to find an eviction set for every color in the cache. So for our tech, the only thing you really have to know is that the technique can also be used for page tables. If you really want to know like the details, I invite you to read the paper. So the 3 challenges are solved. Then it's time again for the big picture, I think. So we have our cache, and we have an AST table, and we have an attacker. And the attacker has an eviction set, but the interesting part of this eviction set are actually the page tables. So what the attacker will do is now a translate phase, where it will simply do something similar to prime, access all the pages, and use the MMU to actually load to fill the cache set. Then it will wait, and the victim will now encrypt something, and that will kick one of our entries out. And then we'll do the probe phase to reload all our entries and see if any of our page table walks will slow down. And we found the page table walk that slowed down, so we now know that this is the cache set that was being used by the AES encrypt. So our evaluation, we tested or checked 3 things: reliability, effectiveness, and the cache defenses. For reliability, we implemented a cover channel to where we basically implemented 6 of the cache attacks, or well, 4 of the cache attacks, sorry. And we measured the bandwidth and the error rate, basically. And the conclusion here is that translate attacks are practical. For effectiveness, we used OpenSSL T-table AES implementation and basically tried to see if we could get a signal with all 6 cache attacks. And you can clearly see that we get a signal for all 6 of the cache attacks, including ours, which means that translate and probe is effective against AES T-tables. And finally, we have the cache defenses. And the question is, does translate and probe actually bypass these cache defenses? So we implemented page calling and a defense using way partitioning. And you can clearly see that these defenses mitigate prime and probe, but translate and probe is able to bypass these. So the conclusion here is that translate and probe is able to bypass both set and way partitioning. So conclusions. We have introduced a new family of cache attacks, translate attacks. We have shown that indirect cache attacks are practical, and we should really reconsider existing cache defenses in software. And if you want to know more about these attacks, I invite you to visit this page. Thank you very much.
Nice. Any questions? Yes, go ahead. Is there a microphone? Yes, state your affiliation and question.
Hi, I'm Kevin Laughlin from University of Michigan. So you talked about way partitioning, and when you're discussing way partitioning, are you referring to partitioning it from either a software or hardware standpoint, or purely hardware? And if that partitioning would be done at the hardware level, have you looked at the performance impacts of these defenses at all?
Okay. So there are indeed both way partitioning defenses in hardware and software. For the hardware defenses, we did not focus that much on the hardware defenses because our argument is that they're not as flexible and the availability is quite limited. For software defenses, we have stealth mem and cache bar, which we considered.
Rick Farrow. Yeah, I was curious. A lot of times I see defenses against these kinds of attacks involving flushing the cache, in between, not between in between different processes. So would that affect your attack?
Yes, I think it would actually. So
Okay.
I'm not sure it would have to be,
I mean, flushing the cache is certainly expensive, but I have seen
Yeah.
that as intended.
If you do that, you basically also flush any of the page tables. So yes, you would be able to mitigate it through that way, but it's quite expensive, as you
Okay,
said.
thank you.
You're welcome.
Hi, Yuval Yarom, University of Adelaide, and Data 61. Sorry. In SEL4, there is an implementation of page coloring that also makes sure that page tables are split between the domains. So the page tables are allocated with the color of the domain. Would your attack work in that case?
If the coloring is also extended to the page table, it would not work. That's also part of our mitigation. So in our paper, we have a mitigation section that also discusses what you could do with the current page calling defenses, for instance, but also way partitioning to mitigate these. And the conclusion was indeed that for page coloring, if you extend it to page tables, then you mitigate this. One of the problems, however, is that page tables are likely not to be the only thing you could use as a compute deputy. So we're also thinking about GPUs that could share the cache with the CPU or the kernel, for instance. So you can trick other trusted components in your system as well. So you really would have to reconsider those.
Thank you.
You're welcome.
Thanks. Any other questions? Okay, maybe while Ben is setting up his talk, I'll ask one more question. So you're measuring the page callers indirectly, right? Did you measure the signal-to-noise ratio? It will be lower than measuring it directly, and how that influences the fact depending on the kind of applications that you're running.
We did not really measure that. So we did not do any checks with where other programs are running or anything. Like we just ran it on a system that we had which was not running much else.
Right, it would be interesting to
Yes.
measure how much like additional noise the environment adds and how stable your channel will remain depending on how you moved it. Okay, let's give Stephan another hand of applause.